Welcome to Vertica Girl. In this video, I'll walk you through enterprise mode concepts. In enterprise mode, Vertica's design goal is simple. Keep your data as close as possible to the compute that processes it. Your data is evenly spread across all the nodes in the cluster, so every node carries an equal share of the analytical work. Every row you load into Vertica ends up in the same place on the disk, which is called as ROS container. Understand this one structure and you'll basically understand how Vertica actually stores your data. Let's decode it. What does ROS stand for? Read Optimized Store. When data lands on a node, Vertica writes it into a ROS container, which is nothing but a set of files on the disk built in the exact format that queries love to read. And every container carries three defining traits. What are those? Segmented, sorted, and compressed. What is segmented? Segmented means the data is split across the nodes of your cluster. So every machine does its share of work in parallel. What does sorted means? Rows are stored in the projection sort order, so Vertica can jump straight to the data a query needs instead of scanning everything. Compressed. Columnar encoding shrinks the footprint dramatically. So less I/O, less disk. So at the end, it's faster reads. So segmented, sorted, compressed. That's a ROS container. Here is the wrinkle. Every load, every batch, every insert can spin up its own ROS containers. If you run a lot of tricky loads, you end up with this. What is that? Dozens of tiny containers spread across the cluster. Each one is valid, but too many small containers means more files to open and more overhead on each and every query you run against the cluster. Vertica even sets a ceiling on how many a projection can hold before it pushes back. It is called as ROS pushback. We'll review it later. For now, just remember the term ROS pushback. So to avoid ROS pushback, what Vertica does, it does clean up itself. And what cleans it? A background service called tuple mover runs an operation named merge out, and it merges those small ROS container into fewer, larger, fully optimized ones. Same data, still segmented, sorted, compressed, but just it's consolidated. Fewer containers and faster queries. One thing I kept flagging on the side there, segmented versus unsegmented projection. That's a topic on its own. We'll decode it next. For now, just remember one thing. Your data on disk lives in ROS containers in segmented, sorted, and compressed format, and merge outs keep them tidy. That's it. Now what do you see on the screen? There are three nodes. Each one holds its own slice of the data, and only its slice. No copies anywhere in the cluster. So it looks lean and efficient, right? Watch what happens. Node 2 fails, so a disk dies, which means a machine drops offline, and the data block it was holding is just gone, meaning it's unavailable at that point of time. So nothing else in the cluster has a copy of it. It doesn't exist anywhere else. So Vertica has to make a decision now. Either hand you incomplete, possibly wrong results, or stop. So it shuts down rather than lie to you. One node down and the whole database goes offline. That's the problem K-safety solves. Keep redundant copies of every data segment on other nodes so that even if you lose a machine or two, the database keeps running. Same data still available when hardware fails. As mentioned earlier, one setting that decides whether your database survives a node failure or shuts down is called K-safety. Let me show you how and what exactly K-safety is with an example. Now we will see how the Vertica cluster behaves when k equal to 0, 1 and 2. Let's start with k equal to 0. Your data is segmented across the cluster. Segment A on node 1, segment B on node 2, and segment C on node 3. It looks clean and simple. So each node is holding a unique slice, and the catch, as mentioned earlier, there are no copies. It's great for storage efficiency, but it's terrible for resilience. So what happens when node 2 goes down? Segment B disappears and no other node has a copy of it. Vertica can't serve a complete picture of your data, so rather than returning wrong results, the whole database will shut down. So one node down, full outage. That's the price of zero redundancy. Now let's set k equal to 1. So when we set k equal to 1, Vertica creates a buddy projection. Basically a second copy of every segment placed on different node. Now segment B lives on node 2 and its buddy B prime lives on node 1. Kill node 2 and nothing stops, because B prime on node 1 takes over for B. C is still safe on node 3. So every single segment still exists on the active node. So the database keeps running. K equal to 1 means you can lose any one node and still stay online. Now let's see what k equal to 2 means. Every segment gets 3 copies of data spread across 3 different nodes. That means 2 buddies for every piece of data. Now lose 2 nodes at once, node 2 and 3, and check the map. Every segment still has a live copy somewhere. A is on node 1 and node 5, B is on node 1, C is on node 1 and node 4. The database doesn't even flinch. What's the trade-off with this? To tolerate 2 failures, you need at least 5 nodes. So the rule is k safety 2, so k equal to 2 plus 1. More copies means more resilience, and you require more hardware. So that's k safety 0, which is no redundancy. K safety 1, survive 1 node loss. K safety 2, survive 2 with 5 nodes or more. So pick the k based on the database uptime that you need. I hope everyone will take a brief overview of ROS containers and k safety. Subscribe and hit that bell icon for more regular updates. Thank you.